So as I said, we're going to talk about friction, drag, and interacting systems. And so let's just get right into it. We're going to have two basic goals, continuing where we were last time. We're going to introduce this thing called the drag force. Again, a lot of you had a pretty good intuition for friction. You're going to find that you have a reasonable intuition for drag as well. These are things that we somehow have an intuition for. And we're going to explore several examples of both friction and drag. And then at the end, we're going to talk about a challenging, very challenging system of interacting objects that we can actually now treat fully using Newton's laws, acceleration constraints, and now these additional forces of static friction and drag. And so we're going to come back to these kind of problems that you see all the time, ropes and pulleys and masses. In fact, one problem that you've seen already quite a bit. So to start, sitting with the people beside you, let's just go to a quick discussion question. This is one that we've seen. So first, stare at it, make sure you're answering the question it's asking. And then you can talk to the people around you. Feel free to discuss. Let's see if we can get it perfect on this one. There are enough people here who should have remembered this, that we should be able to do this one. So take it out another minute. Okay, so I have about 100 responses and about 15 seconds left. So get the last 30-ish responses in and we'll see how good we can do. Okay, so I'm going to stop. Get your response in now. You have 2 seconds. It's not going to kill you. You got it. Okay. Here's what I got. I got 92% said that it was D, or not D, C, that the friction force first increases linearly with my applied force. I get to a point where that object begins to move, it accelerates, and then the friction force remains roughly constant. And we had two different names for these. We had static friction, which is the one that holds the system in equilibrium. And then we broke into what is called kinetic friction. Okay? So I think everybody had a pretty good intuition of this. We had a very simple model for this. It was empirical. And so a lot of questions that I've gotten at office hours and other places is how do we know what those coefficients are? And if you look in the book, it just gives you some numbers, right? What that means is that this is a measured quantity. It's an empirical quantity about which we can't derive anything deeper, right? We couldn't derive it from first principles. Very hard to do. So, but here's the model, right? The static friction, remember, as I apply the force to this object, the static friction applies an equal and opposite force to what I apply. So if I push harder and it still doesn't move, the object's pushing me back harder, right? I have to stay in equilibrium. So this force is less than or equal to some value where it hits a maximum value once I break it into kinetic friction, okay? And remember, it's also proportional to the normal force. When we put more people on that table, there was a larger normal force. It got harder to get it started. Okay? The other one is kinetic friction. And this is the friction when you're already moving. It's a force that opposes the direction of your velocity. Right? So it acts to try to slow you down. And it also is proportional to the normal force. Not the direction of the normal force, only the magnitude of the normal force. And then finally, there's rolling friction, which is the friction basically in any rolling object. We'll talk more about this when we do circular motion, but it's directed opposite to the object's velocity. So think about it. If you had a car with frictionless tires, once you let go of the accelerator, you would just continue at a constant velocity indefinitely. But because you have real tires, you have rolling friction, and the tires essentially act to slow you down. There's other things that are pulling energy out of the system as well, but mostly it's coming from the friction. So here's a question. I started to address this last time, and I want to make sure this is really clear. We asked the question. We have this, what is considered, what I would call an empirical law that tells us that the friction force is proportional to the normal force. And there's this coefficient that's purely experimental. So there's a way that we can actually understand how we get these quantities. And so the question I can ask is, how can we determine the coefficients of static friction for different objects, but also the surfaces on which they rest? Okay? So imagine I took a wooden block and I put it on a sheet of ice, and I took that same wooden block and I put it in a pile of sand. You see that it's both the object itself and its interaction with the stuff that it's moving on. So this mu, this kind of coefficient, has to take into account both of these things. And it's complicated. And so what we do is we instead measure it. So let me come back to how I ended at the very last part of last lecture, and we'll talk about how we can actually do this. Okay? So the question is, how can we measure this when we know that there's no way to derive this understanding? Okay? The first thing we did is you saw this last time. I basically said, let's imagine that I put a block on a ramp. This is becoming now routine. We always talk about blocks on ramps, so you should have seen this before. The basic drawing is, I've done very carefully here. I have a block that when I increase the angle, I'm going to ask, will that block slide or not? Okay? And I've defined a coordinate system where plus x is down the ramp, plus y is perpendicular to the ramp. This is for convenience. Why? Does anybody have a guess? Why is that the most convenient coordinate system for what we're about to do? Are you starting to get an intuition for this? Why did I choose this coordinate system? Well, I heard that gravity is down, which is partially true. What's the direction of motion this object will slide? Down the hill. Okay, so that's one part of the answer. But what's the other part? The normal force. What can I say in this problem? If I have movement in the x direction, I know that I have an accelerating system in the x direction. Is there an acceleration in the y direction in this problem? No. Okay? So often what we do is we align our coordinates to make it so that the acceleration in the problem is only in one direction. Do you see that if I had a coordinate system where x was the normal way we think about it, a horizontal line, the component of the acceleration down and to the right would have both x and y components in that coordinate frame. So what we do is we choose a set of axes that isolates the direction of motion in the direction of one acceleration. Okay? So that's a strategy we'll get better and better at. And if you recall, if I pointed back to this problem of the cart on the ramp, where there's a barrier pushing the cart and holding it in place, we can draw a very similar free body diagram where on this block M, I have the weight, I have the normal force, and I have what is now taking the place of that barrier, which is this static friction. Okay? And again, this is kind of an empirical force law, so we can learn about this by basically doing this experiment. And I'm going to show that in a second. Okay? So here was the basic system. We're going to tilt the ramp. What do you expect? If something has a very, very high frictional force, which means it has a high coefficient of static friction, what do I have to do? Do I have to increase the angle more, or will it start to slide at a less angle?
Increase.
More, right? Imagine I put something very almost sticky, like tape. I put double-sided tape on this thing, but it wasn't perfect. I would have to lift it almost to vertical before gravity was strong enough to take it down the ramp. Okay? So in this angle is embedded the information about this coefficient. And we can basically do experiments to see that. So let's do the theory first, and then we'll try to understand it kind of qualitatively. So here's another conceptual trick that we have to get good at in solving these problems. And I've said this many times. We have to imagine the motion. We have to imagine what would happen in this problem. So if you think about what would happen, I would increase this angle. So I'm tilting the ramp more and more and more. And at the maximum angle, just before it started slipping, I know that the system's in equilibrium, and I can extract this value of mu s that keeps it there, right? So what I have to imagine is that I increase to some maximum angle, and right before it starts slipping, it's still held in place. And what does the sum of all forces have to be? 0, right? It's in equilibrium. Once it starts moving, then I have a sum of forces that equals mass times acceleration. But in this instant, right before it slips, I can use equilibrium, which makes the mathematics a little bit easier to do. So let me do this. Here's the first part. And again, by now we're getting pretty good at this. The first thing I'm going to do is take the sum of all forces in the x direction. Remember, my x direction was down the ramp. Okay? So if I do that, maybe I'll zoom out so you can see the picture a little bit better. Okay? If I take the sum of forces in the x direction, I have, what's the force that's pulling me down the ramp? Fundamentally, what is the force? It's gravity. Okay? But we've done this many times. It's some component of the gravitational acceleration that gives us that force. So that component is basically the weight times the sine of the angle theta in this drawing. So that's pulling us in the positive direction, minus the frictional force, and I have it sub s, which is the static friction force. Okay, so that's this, I just added up all my forces, and I set them equal to 0. So in doing that, I get my first expression. It just tells me, I'm just doing some algebra, that the static coefficient of friction times the normal force is just equal to the sine of this angle, theta. Okay? So that's just algebra applied to the system after Newton's laws. Now the other bit of information that we have to work toward is looking at Newton's laws in the perpendicular direction. So in this case, we called that the y direction. Remember, we said y wasn't straight up. It's actually this normal direction in this picture. You can see it here. It's the normal direction to the right. So we take the sum of all forces, and again, we have the normal force pointed in the positive direction, and minus this component of the weight, which is weight times cosine theta. Okay? And again, does this accelerate? Does the block ever leave the ramp in this problem? No. So there's no acceleration in the y direction. I can set that equal to 0, and I get another equation that the normal is equal to weight cosine theta. So now I have two equations, I have two unknowns, and so I can basically begin to solve. And the way I do it in this problem that's most efficient, I want to understand this static coefficient of friction. I want to ask, how is it quantified in this problem? It's basically the weight times sine of theta, this comes from the first equation, divided by the magnitude of the normal force, it's this piece. And I know from the second equation that that n is equal to weight cosine theta. So I get this expression, weight sine theta over weight cosine theta. If you notice, one thing that's kind of unintuitive is that mass doesn't matter in this problem. I basically, mass and the g, little g, is embedded in this weight, but it's divided out. This often happens in these problems. Mass is not going to play a role in our static coefficient. And what I get just from trigonometry is that it's just the tangent of some angle. Okay? So now I have a way to think about how these measurements might work. I know that the static coefficient of friction is going to just be tangent of the maximum angle that it takes for that block to begin sliding. Okay? So let me show you two examples. Again, just qualitative. We did this last time, but I want to show it again with some slight variations. I have two blocks. They're the same mass, same dimension. What I've done is I've just changed the surface on one of them and how it interacts with the table. Okay? So I have one that's untouched. It's just a wooden block that's painted. The other one, I've taken something that's kind of rubbery. It's electrical tape. It's a black, rubbery kind of tape that you use when you're wiring things. And what it does is it should, in principle, increase that coefficient of static friction. So I'm going to try it. I can't promise anything. Well, here's what we're going to do. I'm going to lift. I'm going to wait until I see one of them start to go. That will tell us that maximum angle. And we'll ask if it's bigger or smaller. You should see, slowly, tell me what it goes. Now, what happened to it when it slid? How did it slide?
Very, very fast.
It went fast, right? There was a very high acceleration. Did it topple or did it slide? It slid, okay? So why did it do that? What's the difference between these two blocks from this new way of measuring it? What was the difference? The one without the tape slid at about half the angle of the other one. that's a number. I can take the tangent of that number, right? I could say one maybe happened at about 30 degrees, the other one was almost 45 or 50, and that gave us a number. Do you see how if I wanted to tabulate, I wanted to say, give me a whole bunch of materials and ask how they interact with a smooth tabletop, I would just measure that angle that they start sliding, and I get an instant quantification of mu sub s. So when you go in your textbook, you'll see a table of weird materials or what they're interacting with, and you'll just get a number. Okay? Now, I want to do one more and see if it works. Let's try it. Now, what did I just do? I put chalk on. What do you think that would do to the coefficient of static friction? It should lower it, right? If you've ever, has anybody ever been in the, I guess it's maybe Boy Scouts who do this, there's a thing called the soapbox derby. It's a little car race that you roll a little wooden car down the hill, okay? When you do that, what all the cheaters do, I don't know if they're cheaters, but they do this, is they fill the axles of those wheels with powdered graphite. And powdered graphite, even though it's dry, it's like a powder, it's a lubricant. So it allows those wheels to spin with much, much less friction. So the hope here is that this one that I've just completely dusted with chalk should go quite a bit sooner than this one now I'm not using the tape side, just the normal side. Let's see what happens. So what happened? What did I do by adding the chalk dust? I just changed the coefficient of static friction. So you see how empirically this law gives us everything we need to create a table of everything. I could write a table of wooden block with black paint and powdered chalk dust, and I get a number. And I could put Nike shoes with gum stuck to the bottom, and I would get a number. So because we can't derive it from any deeper principles yet, we have to do this. This is what we call in physics an empirical law. But do you see how we derived it from a situation that you all know now extremely well? It's just the idea that I have forces acting on an object that are in equilibrium. So I could give you all sorts of different ways of measuring these coefficients, and it would have to be essentially carefully understood from Newton's laws. Okay? Any questions on that before we move on to drag? Okay, good. Let's go. So there's another kind of force that we're going to talk about, and that is the drag force. And it's actually quite similar in some ways to, there we go, to this frictional force. So who's ever seen these types of pictures? Who's ever been in an automotive wind tunnel? Anybody ever been in one? Okay, they're pretty cool. So basically what they're doing in these images is the car is sitting still in a wind tunnel. And a wind tunnel is just a tube where they blow air at very, very high speeds that they can change with some big fan. And what they do is they blow these little smoke streams. These are just usually kind of some heavy, it's kind of like the fog machine fog that I gave you, that I poisoned you with a couple weeks ago. You use this fog to basically track the flow of air around this object. Right? So what you're seeing here is, up here, it doesn't really interact much. There's a little bit of a pressure gradient, so it kind of bends around the top of the car. But then when you hit the front of the car, these airflows get compressed, right? They get squeezed toward the car. And then if you look behind the car, what do you call this stuff? Probably have seen this before. Turbulence. Who's ever been in an airplane and felt turbulence, right? Turbulence is this chaotic movement of the atmosphere, of the air. Who's ever heard of drafting? Anybody go to NASCAR races? Everyone ever tried to draft behind a tractor trailer? It's considered one of the most dangerous things that people actually do on highways. So drafting basically occurs when these eddies of current behind the car are basically drawing a big loop, and the force is toward the back of the car. So in NASCAR racing, what they often try to do, it's a very common strategy, is you try to race about 2 to 3 inches behind the car in front of you, in the hope that they're wasting all their fuel dragging you along behind them. So this is called drafting. So often what you'll see in these races is that they sit behind that car as close as they can. When they find a point that it's an opening or on a turn, that's when they accelerate past. So often in that racing, you'll see that they're taking advantage of what's called drafting, which is the turbulence due to drag. Okay? But the drag force is actually much simpler. It's the force that is constantly slowing you down. If you're driving this race car, you have to design these cars for several different things, one of which is reducing the drag force. Right? So who's ever looked at a Corvette? Right? What's the basic thing that you see when you see a Corvette or even a Lamborghini? It's often or a GT30 or GT4. They're very, very low. They're short. They're very wide. They have a wide wheelbase. Why do you think they're so short? Exactly. What I see is this. He did this motion with his hands. When I want to think about the airflow over the Corvette, I don't want it to hit a wall. I want it to move over the Corvette without creating a drag force. Who's ever seen a tractor and trailer truck? When I was a kid, they all looked very different than they do now. This wasn't even that long ago, but here's what a tractor and trailer truck basically looked like. Without the trailer. Okay? What do they look like now? Do you notice? All of them have been basically polished to be round. And when they have this trailer on, which is generally higher than the truck, they put a little dome on top of the truck. That never used to be there even 20 years ago. Every truck has this shape. Why are they adding this kind of funny shape to the truck? To reduce drag. Why would you be interested? If you were a truck driver, you get paid per mile, you pay for your own gas, and you generally drive really long distances as fast as you can. Why would you be interested in buying a truck that looks like this rather than a 20-year-old truck? Fuel efficiency. Okay? So drag is the major problem. Does anybody in here drive a Prius or a hybrid car? Yeah, I have a couple. Wait, here's what does anybody in here actually drive the Prius at 55 miles per hour? Okay, here's the problem with the Prius. Watch your fuel efficiency. Once you go above 55 miles per hour, it dies like crazy. Okay? We'll see why. When you speed up, the drag force gets stronger and stronger and stronger. So a lot of people think, oh, I'm getting, I don't know what these numbers are now, 35 miles per gallon. If you drive at 55, you'll get a lot more fuel efficiency, but you'll look like a crazy person in Southern California. So here's what we've got. So now, you have an intuition for this. The drag force is always opposite to the velocity of the object, and it increases in magnitude as the object's velocity increases. Wait, here's a question. When I'm in a wind tunnel with this car, am I actually moving the car? No, I'm moving the air. There's a velocity relative to the car that is high, and that creates a drag force on that car. What's keeping that car from moving? Say it again. Static friction, right? It is stuck on this road with tires that are holding it in place. So when we talk about drag, we don't just have to think about an object moving at a velocity v. It can be that the object is still and the air is moving past it at a velocity v. This is a question of reference frame. Okay? And we'll give some examples of that in a minute. But drag is very similar to friction. It's basically a property of the fluid that you're in. It's a property of the interface, what shape you are. But it's basically coming from kind of the push of these air molecules against you, creating friction. So when I move through a fluid, whether it's gas, liquid, whatever, there are frictional forces. There are things that are basically determined by, again, empirical laws. They tell how the kinetic friction of a molecule moves past this object. There's force needed to basically push the fluid out of the way. So if I was looking at a block in water, these are little vector flows. The water would have to go up and over that block to actually get past. That requires extra force to push it up or down. And then there's properties like the viscosity of the fluid. So again, drag is like friction in that it's complicated. And so we can't write down a fundamental law. There's no famous scientist whose name is given to the theory of drag because it's an empirical law. There's no way to derive it from kind of microscopic principles. So we have to create a model. And it's just like friction. You'll see how it works in just a second. So here are a few assumptions. And these are really important for the types of problems that we can solve. So the object size is what we would say macroscopic. So it's a few millimeters to a few meters in size. Okay? If it gets too small, the fluid behaves very differently. If I'm as small as molecules, it doesn't look like a continuous fluid anymore. I'm being pushed around by the molecules of gas in the air. So it doesn't work at very small scales. At very large scales, again, the fluid looks very different. And we have a quantification for this, I won't get into it, but when we think about fluids, there's a number called the Reynolds number that basically describes whether it's you are big compared to the fluid viscosity or small. And it's complicated, so we won't do it here. Now the object's speed has to be slow. Okay? When we have really, really fast movement through fluid, has anyone ever seen a shock wave? Right? Who's ever heard a sonic boom from a jet? Has anyone ever heard a sonic boom? When you hear a sonic boom, what's happening is that the jet has broken the speed limit of sound in air. And when it does that, it basically creates a pressure shock that's a concussive shock, and that goes radiating down to the ground. It sounds like a giant crack of thunder. In that case, this normal model of friction is completely useless. Okay? When you're exceeding the speed of sound, the model we're going to talk about does not work. Okay? And the object has to be moving through air roughly near Earth's surface. So we're even going to just say, look, this is kind of normal aerodynamic forces that you might see in an airplane or a fast-moving car. And here's what it looks like. Okay? Now this has a really interesting form that we have to study further. First of all, notice that it's a vector. Which direction is that vector always pointing? Opposite the velocity. You see it's embedded here, there's a minus sign, and there's a v hat, which tells us if I can draw the velocity vector, I know that the drag is always opposite the velocity. And that's completely consistent with what we've already said and our intuition. Now on top of that, there's a couple extra parameters that we have to study. So one of them is just called the drag coefficient. This is like friction. This is the thing you have to measure. You have to look at an object and guess or measure what its drag coefficient is. When I left the last lecture, I asked who's ever put their arm out the window in a speeding car, and I turn my hand this way, and I kind of get some lift, right? I can do what's called an angle of attack in aerodynamics for aircraft. As I tilt my hand up, what happens? You start to feel lift, okay? If I put my hand sideways, I have to create a humongous force to keep my hand in place. That's basically increasing what in this equation? There's this drag coefficient, there's this other one called what? Cross-sectional area. So how do parachutes work? Why does a parachute work? It's basically you're creating drag with a large cross-sectional area. And it slows you down. The more that area is, the bigger my parachute, the easier it is to slow you down. Okay? And then there's this thing that depends on the density of the air, or the air fluid. Did you ever watch? I should show you this video next time if I remember. There was a GoPro video of a man who jumped out of a weather balloon, basically from the fringes of space. Have you seen this? Oh, some of you have. I will show it next time because it's ridiculous. He basically takes a weather balloon up to the very fringes of the atmosphere. There's very little atmosphere, so little that he actually has essentially a spacesuit on, and he jumps out of the capsule. Okay? And he can't parachute. There's a long period of time where if he even had a parachute, it wouldn't work because the density of air is so low that it provides no drag. So there's a point in his fall where he starts tumbling uncontrollably. He has GoPro video of his point of view spinning and tumbling through the air as he can't do anything because it's too early to put out the parachute. Once he gets low enough and this density is big, so he gets to kind of where the air is thicker, basically he can begin to slow down and he puts his parachute out. I'll show it to you next time. So let's ask a question to see if we get it. This is pretty straightforward. This will make some of you feel guilty. This is a loaded question. Which automobile has the lowest aerodynamic drag coefficient? Okay. So look at these vehicles. I've already delivered it. I see already 9 responses. Take about 30 seconds and tell me which of these vehicles has the lowest aerodynamic drag coefficient. Just guess. Okay, so about 5 more seconds. Okay, 2, 1, 0. Okay, I'm going to stop. Here's what I got. 76% said that the lowest aerodynamic drag coefficient is B, the Honda Insight. Does anybody drive? Probably not a Honda Insight, they might drive Honda. Or any car that is in this class. There's a whole bunch of them, right? There's the Toyota Prius, there's now several others. Why do we drive those cars here? Why do we drive cars that have lower aerodynamic drag coefficient? Well, there's all kinds of excuses. The real one is that you probably are trying to save money in the short term. Okay? You're saying, I want better fuel efficiency, and it's cheaper, and gas in California is the most expensive in the union, and it sucks to pay a lot for gas, so why not have a cheaper car? Yeah. That's just the direction of the vector. So if I have a vector drawn on an image, let's say I create an axis. I can call this the Vx hat direction, this the Vy hat direction, just like we do with normal coordinates, x and y hat. And I'm just saying that I can have a vector V, which has a magnitude and direction, but it's in what we would call the V hat direction. So if you go back to math, you should all have seen this before. These are called the unit vectors. It's actually in chapter 1. So it's always opposite the vector. Yeah, exactly. It's opposite the vector velocity. Okay, so going back to this car, one of the things we tell ourselves is that we're trying to save money and we're trying to be earth-friendly, etc., etc. What is the actual problem with these cars? Anybody know? It turns out that the battery that you use to basically operate your hybrid or fully electric car is filled with some of the heaviest and most dangerous metals to put into a landfill. And where do you think those batteries go? Into a landfill. Okay? Sometimes truth hurts. It turns out you probably are helping to save the environment a little bit, but not as much as the marketers and salespeople have told you are. Okay? So I would say physics, if nothing else, should teach you how to not be deceived. Now, let's do one more. Which automobile has the largest aerodynamic coefficient? I think it's probably obvious. The governor, your former governor, would have known. So take 30 seconds. What?
And then it's not.
It's the unit vector. You look up unit vector. I usually call it a half. Okay, so let's see. Okay, here's what I've got. 92% said D, the Hummer. Okay, good, you're getting it. Does anybody drive a Hummer? Yeah, you probably wouldn't raise your hand if you did. No, I drive a Tesla or whatever, right? Okay, these have basically been villainized because they essentially guzzle gas. Part of the reason they do, these are, in my opinion, terrible cars to drive, especially in California. These, in fact, have a terrible drag coefficient, and they get something less than 10 miles per gallon, 8 miles per gallon. An M1 tank, does anybody know what the fuel efficiency of an M1 tank is? So this is about, a few miles per gallon. An M1 tank isn't that much different. It's a few gallons per mile, right? It's maybe an order of magnitude less. Tanks, they're heavy, they're not designed to be aerodynamic, they're not good for fuel efficiency. They don't have good drag coefficients. Okay? There's other things the tanks are designed for, but we won't talk about it here. Now, we've talked about cars a lot, but I want to point out a short video that shows that this isn't the only thing that we can use to manipulate our forces. Has anybody ever seen? What's this thing called? It's a flying squirrel suit or a wingsuit. Okay. Shh. Let me see if I get the volume on here. See if I can get the volume. Check this out. This is an incredible video. Again. Let me turn the lights down.
70, 70.
So he said that path is a little more than a meter wide.
Dopo lo schianto di ieri.
Now, what do you think the purpose of his wingsuit is?
Il nuovo, questa volta dall'altra parte, spostare in questo modo.
What's that? Watch what he does. Yeah. Here he goes. And then the ad there, if you're interested, is how the world works. Okay, watch. Okay, watch really closely. This is the most incredible thing. That means maybe about twice as wide as an arm span. Who would do it? So what was he doing? He was effectively manipulating the drag force. He basically has a way, this little funny suit, that allows him to change both his cross-sectional area and his coefficient of drag. Do you see that it basically allows him to steer? Why would it be able to steer you? Because he's turning not just the magnitude of the force, he's changing its direction. His arms, the subtle movement of his arms basically change the vector velocity of the airflow. Let me show you one more demonstration. Let me get the better lights here. Now, that was an object moving very fast. Right? He was moving very fast through air that was effectively still. There's another really complex situation that I can show you.
Mega vacuum.
See if I can do it. Hold it still. It might not work this time, but watch. Why? This one's better. Okay? What's going on? This is actually really complicated. I'm going to give you the simple story for a second. You see that eventually this thing comes into equilibrium. There's a little bit of acceleration, but it's basically accelerating about what there goes, and about there.
Hey.
Okay, so what was happening? What was the force pulling this object down?
Gravity.
Gravity. What was the force pushing it up? It was drag. You could say that it was the force of air on this object. But remember what I said about these cars in the wind tunnel? They were being held in place by static friction. They were still, and they were using the velocity of the air to measure drag. Okay? What I just gave you was a problem where the object wasn't moving fast in your reference frame, but the air was moving past it very, very fast in your reference frame. Okay? Let me give you an interesting piece of physics, which you'll do in Physics 2B, I believe. There's actually a subtle piece of this. This is a really interesting piece of physics. But here's the ball. Here's what the airflow looks like. Just like in a wind tunnel, if you imagine this ball displacing just slightly from the center, what would you expect should happen? It should fall off the airflow. Why did it not do it? What does it say about the forces? I saw arrows being drawn. What are the forces acting on it in the horizontal direction? If it's held in equilibrium, there has to be an equal and opposite force on both sides. When you get to fluid dynamics in 2B, you're going to learn that this is called the Bernoulli effect. Okay? When I blow air past an object, it reduces the air pressure, and there's a force from the other side pushing on it. In this case, air is balancing. It's forced to basically ride on top of this flow of air. So you saw a combination in this demonstration of both a drag force because of the velocity of the air, and it basically fights gravitation, and you saw this lateral force or horizontal forces that are coming from the Bernoulli principle, which we can't really talk about here. Okay? So now, in the last few minutes, we have now a sophisticated set of skills. This is the last lecture we'll talk about these systems. Now we'll start to talk about circular motion and apply these laws. But we can now explore what happens in essentially real-world systems. We're getting better and better. We have lots of different forces we can think about, and you can start to think of these interacting systems in more and more places. But before we go into anything complicated, let's go back to an example that we started, but that can actually be made super, super complicated. Okay? Here's a system. You've seen this system before. We went through this problem, and we'll talk about it a little bit. But here's a block on a ramp at some angle, and there's a heavier block on the other side of the pool. Do you remember we started this problem? What did we assume in that problem? We basically assumed that the rope was massless, we assumed that they had an acceleration constraint, and we assumed that there was no friction in the ramp. Okay? Here's the type of question that could easily show up on an exam. The figure shows a block of mass m resting on a 20-degree slope. The coefficients of friction with the surface are mu sub s and mu sub k. So again, these are numbers that are given to you, right? There's a static coefficient and a kinetic coefficient of friction. It's connected via a massless string over a massless frictionless pulley to this hanging block. Here are the questions, and these are hard, but completely solvable at this point. What is the minimum mass m that will stick and not slip? Right? So given these frictional coefficients, what friction force do I need to basically keep this thing from moving? What's the one easy part of this problem? What's the first and most important thing that you have to recognize about this problem, where it asks, what is the minimum mass that will stick and not slip? It's static, okay? So when I apply Newton's laws, what does that tell me about my net forces in that problem? They sum to zero. That problem is slightly easier than the next, which is if this minimum mass is then nudged and begins to move, it will start moving up the incline. What is its acceleration? Okay? Do you remember we solved this problem already, assuming zero friction? We went through and found that acceleration. Now we are completely sophisticated, where we can start to ask questions with friction. Now, let me show you the solution to the old problem, just so you remember roughly how we did it. And you'll see why this one is different. Let's see if I can get that to work. There's one, there's the other. Here's the solution. Let me just give you the solution, because that's what sometimes you guys are always after. Okay. Here's the solution with these masses. Again, this was frictionless, and we asked what's the acceleration of the system And we saw that it depends on how big the big mass is and how little the little mass is, and it depended on that angle. Is there any way from this to answer the question that I just asked about friction? Does anybody think you could just plug numbers into this equation and get the answer? Never. Okay, that's not how physicists think. That's not how we test you either. When you treat this problem, you have to go back all the way to where we started, right? We go back to these free body diagrams. How do I implement, how do I ask where these frictional forces are important to draw? How would you draw it for the first question, which is, what is the magnitude in order to keep it sticking? What is the force that's missing in this left diagram? I have the tension in the rope pulling up, I have the weight, I have the normal force. What's the one that's missing? The force of static friction. If I added another static friction force, it always opposes my direction of motion, so I would assume it's going to roll up, and I would say friction is pulling back and down. And then when I sum all the forces, what are they equal to? They're 0, because the question said it's stuck. So I would have to sum all the forces here, add them up, and set it equal to 0, and I would have to do the same thing over here. So immediately you see that going through these steps that we went through, which I'll just show you very quickly at a glance, you have these in your notes. Basically, we had to do Newton's laws. We had to apply second and third law throughout very carefully. Now you have to add these additional forces. Okay? Getting finally to this last question, what's the difference for this last question? How do I work through this problem if I now assume that it's moving through the system? It means that the sum of forces is equal to what? Mass times acceleration. It's the same rules. I draw a free body diagram, I write all the forces down. The only difference is that I now know that the system is accelerating. Okay? I'm not going to solve this problem, so either talk to the TA or ask Nick, work through it yourself. You should be able to answer problems like this. You'll see problems like this in your homework.